Okay, today we are going to problem 11.3 and 11.4. Show explicitly that two successive Lorentz transformations in the same direction are equivalent to a single Lorentz transformation with the velocity below. This is an alternative way to derive the parallel velocity addition law. To be explicit, consider a Lorentz boost in the x0, x1 plane with the velocity v1 from the unprimed to the prime frame, followed by a boost with velocity v2 from the primed to the double prime frame. When we combine this give the two relations below. If this were a single Lorentz boost, then we must be able to write it as radius x0 prime prime equals gamma 12 times x0 minus beta 10 x1, and x1 prime prime equals gamma 12 times x1 plus x1 minus beta 12 x0. Comparing the two expressions gives beta 12 equals beta 1 plus beta 2 over 1 plus beta 1 beta 2, and omega 12 equals omega 1 times omega 2 times 1 plus beta 1 beta 2. The first term gives the desired velocity addition relation. However, for the second term, for consistency, we also have to show that the second term is consistent with the Lorentz boost. To do this, we consider the square. We open the gamma 1 and gamma 2. And after the calculation, we can find that the second term equals to gamma 12 squared. Hence, this is indeed consistent with a Lorentz boost. Alternatively, the velocity addition relation can easily be seen in terms of repeatedness for boosts in the x0, x1 plane. We write down the matrix delta 1 and delta 2. And by matrix multiplication, we see that the composition of two boosts is then delta 1, 2 equals delta 1 times delta 2. And since repeatedness zeta I are related to velocity beta I according to beta I equals tanh zeta I, we have simply zeta 1, 2 equals zeta 1 plus zeta 2. Or beta 1, 2 equals tanh times arctangent beta 1 plus arctangent beta 2 equals beta 1 plus beta 2 over 1 plus beta 1 beta 2, which is identical to the result found above. Finally, note that two successive Lorentz boosts in the different directions generically gives rise to a Lorentz boost along with the rotation. This is related to the non-abelian nature of the Lorentz group. And for problem 11.4, a possible clock is shown in the figure. It consists of a flash tube F and a photocell P shielded so that each views only the mirror M located a distance d away, and mounted rigidly with respect to the flash tube photocell assembly. The electronic innards of the box are such that when the photocell responds to a light flash from the mirror, the flash tube is triggered with a negligible delay and emits a short flash toward the mirror. The clock thus ticks once every 2d over c seconds when at rest. Problem A. Suppose that the clock moves with a uniform velocity v, perpendicular to the line from Pf to M, relative to an observer, using the second postulate of relativity, shown by explicit geometrical or algebraic construction that the observer sees the relativity's time dilatation as the clock moves by. Time dilation. The perpendicular motion is fairly easy to handle if the box moves to the right at a uniform velocity v. We have the situation shown in graph. Denoting the round trip time t, the box moves a horizon distance of vt during one complete period. Using a bit of geometry, the distance d traveled by a beam of light from the box to the mirror and back is simply d equals root 2d squared plus vt squared. For a constant speed of light, this gives ct equals root 2d squared plus vt squared. Solving this for t gives a familiar time dilatation expression t equals gamma t0, where gamma equals 1 over root 1 plus v squared over c squared, and t0 equals 2d over c. And for problem B, suppose that the clock moves with the velocity parallel to the line from Pf to M. Verify that here, too, the clock is observed to tick more slowly by the same time dilatation factor. Here, consider a space-time diagram as a graph. Here, the box is moving in its parallel direction. We ought to note that this gives rise to a length constriction d to d over gamma. However, for now, we simply suppose that the box mirror construction appears to have length d prime. The light beam reflects at position y retarded at time t retarded, and is recaptured by the box at time t. We first work out algebraically from the figure. The mirror's position is given by y retarded equals d prime plus vt retarded, while the light ray travels according to y retarded equals ct retarded. Solving this set of equations gives y retarded equals d prime over v minus v over c, t retarded equals d prime over c over 1 minus v over c. And on the return, the light ray is captured by the box at time t and position y equals vt. Noting that the return path of the light ray is given by y equals 2d prime over 1 minus v over c minus ct. We equate this to vt to obtain t equals gamma squared times 2d prime over c. Here we realize that if lengths are constructed d prime equal d over gamma, then t equals gamma t0 gives the same time dilatation factor as part A. Alternatively, by demanding that the time dilatation factor is universal, we may obtain the length contraction relation dpi equals d over gamma as a result of this computation.